I can finish. So I had a lot of difficulties for those of you who'll be hearing it later today in getting the session started for last 40 minutes. So I wanted to cover the solution for homework 2 and also get into clustering, which will be your homework 4. It's a very interesting topic, clustering. So if I cannot get to clustering today, and homework 2 solution takes a longer time, then we can just have another session, maybe this weekend on Sunday, to go over the clustering part. So for your homework 2 solution, I will not review the task 1 solution because I want to look at your homework that you have uploaded individually and just kind of follow how you are doing there and give you specific comments. So you will get comments for me for task 1 based on your submission, but let's review the homework 2 solutions. In homework 2, we have 5 self files that are lean as subjects, and the other 5 self files that are from diabetes, right? And you're supposed to do some comparison of this and do some t-test, p-value, draw some volcano plot. So all this you have already read on your homework, so I'm not going to go over that other than the solution that I'm going to cover. So the first thing that you need to do in any of your homework is create a folder where you're going to keep all your self files. So for my case, I created a R1 folder, and in my R1 folder I have 10 of my self files. So when you went to the website where I gave you the location, it was probably at the beginning here, the URL that where your self files are located, they probably were zipped file with .zz extension. So you need to unzip those files, and you probably had more self files than I asked you to in the homework, but you can unzip those self files, and the ones that you need you can move to your working directory from which R will be pointing R, and from which I'll be working. The next thing that you need to do for your assignment is you need to create a covdesk.txt file. So let's go to where I kept the covdesk.txt also. So this is the covdesk.txt file that I prepared. So let's open and review it. So the criteria for this excuse me, covdesk.txt files are, you have to indicate for each file what condition they belong. So this is a space delimited file. That means you have a space here, that's your second column, and you have your self file, you have space, that's your second column. So the first column will not have any header, that will only include the self files. So I have 10 of them, and they have to be exactly named with .cell extension as they have been named under your, in my case, the R1 folder where I have kept my self files. Then the treatment condition, for my case, I have the first self file is lean, so I noted them as L. The other 5 self file came from obese, so I noted them as O. So it's L and O. So treatment column is the header for this L and O. So you have to keep this covdesk.txt and the same directory where your self files are. So I have my covdesk.txt and my self file. So now let's jump into R for the solution. So let me clear what I was showing before. So clear the console. So the first thing is I point R to the working directory, which is set working directory R1. Okay. So even before I go to the first thing, I have had some comments from some of you where you did not have, you had challenges in getting the bioconductor packages. So in case you are not reading the lectures, this is what you need to do is under lecture 4, actually I give you the detailed instruction on how to download bioconductor packages. So you have to be first connected to internet, and then second is you have to issue this command called source that connects you to the bioconductor, and that comes with some specific base packages. So in addition to those base packages, for example biobase, if you need simple FE, if you need FEPLM, etc. So for each of those packages you issue this command bioclite, and you put the name of the package inside a double quote. If you want to keep multiple packages at the same command, you can just do it by, so if I want to import both FE and FEPLM, I can separate by a comma, and I can issue the bioclite command. So BioC-Lite source being connected to internet. So that's the first struggle, rather to say, that you have to overcome. So all your packages are there. In the homework solution, I don't do that because I had already imported the AFI package and simple AFI, and I don't want to spend another 5-10 minutes, again re-uploading that. But you should be able to do that from your own workstation. So now that you have your packages, right? So what I would do is I set my directory. So as I showed you, everything is in the R1 folder. So I set my directory in R1. One very convenient way to figure out what's available on your R1 folder is to issue a dir or directory command. So once you do that, you can see that, okay, I have my 10 cell files. I have my covdes.txt. I have seen in the past semester and also this semester, depending on the Windows version you use, I don't know, maybe Windows Vista or something. What happens when you upload, I'm using Windows XP, but if you may be using Windows Vista or some other operating system, when you save a text file like a notepad, it actually by default saves it as a .txt. So if you want to again save it as .txt again, it probably saves that .txt two times with the same extension. So you actually have to be careful that you're not naming it as .txt a couple of times, because if it's got saved as .txt, but you're trying to read a .txt file, it will not work because R is case sensitive. So every single letter on the name of the file has to match. Okay. So now you use the command, so you load the library. So in my case, simple AFI is already available, so I don't have to use a source and BioC-Lite. So you load the library by library simple AFI. One of the first thing that I do, and I also told you in the homework, is try to understand what are the different functionalities that's coming with the package already. So a very quick way to do that is the library help equals to simple AFI, and I will remember not to do that because as soon as I do that I'm going to get kicked out of DimDim, but it was on your homework. So once you do that, you should be able to see what are the different methods that is available, and where exactly your files are getting saved. So let me also show you that. So in R, each time you load a library, it will give you a path where the different codes and the vignettes are getting saved. So I think it's most likely for a Windows-based system, it will be program files. Then you can go under R. Then R2.0, then these are all the and under libraries. So these are all the different libraries that I have imported so far. So your simple AFI actually got imported here. So under simple AFI, if you go to doc, you can actually find your vignette simpleafi.pdf, which I actually also uploaded and gave you with the part of the homework, plus some additional documents like QC simple AFI, etc., etc. Right? So now you need to now read your particular 10 cell files, and you already created the covdes.txt. So these are the things you need. You need your cell files while creating those covdes.txt. The first column will not have any header, and I already showed you, how covdes.txt files looks like. So then you issue the command read.afi. It's already on your vignette. So if you open the simple afi vignette, so let me do that. So under web session 5, I have the simple afi vignette. So simple afi vignette itself actually gives you step-by-step direction, how to process it, and most of you were able to follow it. And let me just take you to the exact line where the code is. So that's what we did, right? We did the library simple afi, and this is the file command that we'll use, read.afi function. So once you use a read.afi function, it actually reads all your cell files and creates an expression set object. So inside the read.afi, if you give the covdes.txt file description, then in addition to create an expression set object with an assay data, it also creates a data for you. So it will know actually which cell file belongs to which condition. So that's why I think it's very important for you to understand the last lecture and do the task 1. So when I get into this vocabulary of expression set object, ASA data, Fino data, annotation, you should be able to connect, right? What exact particular object that I'm referring to and what is that we are creating. So that's the function. So let's do that. Let's do read.fe conf.tst. So it got read, or it's reading. And as I mentioned earlier, since my recording is a Java-based program which is using a lot of memory, and the R is also requires memory to process its own. And being this is a laptop, not a server, there it's actually slows down because we have a limited resource I have in my laptop. But if I do not share the screen, if I just simply work with this R folder, with the R application, it's not as bad. That's why when I show it to you, it's just always slower because I'm recording and a lot of threads are being used in the memory. So while it's doing that, there's another file I want to open, which is the QC file to explain how QC works. And you should be able to follow that too. So R, so if you go to doc, other than the vignette, this qc.simplefe.pdf, this particular PDF file explains the QC concepts quite well, and which we will come to in a moment. So let me open that also. And this is still reading. Very, very slow today. And now it's not responding almost. Hmm. Just give it a minute more before I kill it and start again. It's a very memory intensive operations. So I think I'm just going to reload it again. Okay. So do the R. Because you have the dim, so on top of which is sharing my screen, then I have the echo capture, which is recording what I'm doing, plus I'm running a program on my laptop. So these three things in parallel slows down each other. But I don't have any other alternatives other than this. Okay, so let's open the script again and go very quickly. So even here it doesn't open. Okay, so we want to do this one, homework 2, task 2 solution. Open. Okay. This is really painful. Sorry guys. It won't work from here. So what I need to do is maybe I can just put it under this. Okay. All right. So let's zoom through this. It's a little better. Okay. So again, so I set my directory. Maybe I should just go very fast. Try to explain a lot, maybe wasting time. So you can figure out what your directories are. You load your library that you need. You created your covdes.txt file. So it's loading the library. It's extremely slow. I did not have this problem last semester, so I'm not sure what has changed. Whether it's DimDim is using more memory or not, I cannot tell. Okay, so it loaded the library. So now I'm going to read and create an expression set object based on the read.fe function. So let it run for a minute or two. Okay, good. So you'll always get, when you have a text file, the last line, because of a carriage return or whatever line that marks it as the end of the file, you get this error. So I wouldn't worry about it. So you can exclude it. So what I left off is each time I use a method in a particular package, I want to know what kind of class it created. So in your scenario, you're expecting it to be an expression set object. So figure out what the class is. So class in your scenario is AFI batch object. Now, if you do a help on AFI, which I cannot unfortunately do because I get logged out from DimDim, the AFI batch object is actually an extension of the expression set object that you created on your task one. So your base expression set object is AFI batch is an extension of that. So what I mean by extensions, if you look at the structure of this, the raw data or the AFI batch object, it will look similar to you when you created the expression set object. It has the same pheno data, asset data, feature data as a slot, experiment data, and protocol data, and annotation. So this all we already showed you in last web session. So what it has in addition is another slot called class version. It also has a slot called CDF name, number of rows and columns. So these are the 4 different slots that AFI batch object has in addition to the expression set object or ESET object. So it's just a simple extension. It's the same thing. It added few more slots. So that's what the AFI batch object is. So now that you read your raw data, you know it's an expression set type of an object. You looked at the structure. You can look at the help file to see what are the different functions that's available under the AFI batch object itself. So now we will transition into QC. So under the simple AFI object, you actually also can do a QC, and it gets stored in a class of type QC stats. So let's just first do the QC, let's do the plot, and let's understand what that plot means. So you use the function QC, and then let's do the plot, and I will take you through the plot. So this I won't need, so I'll close that. Again, apologies for it being slow. I can probably finish this whole script if I wasn't sharing like in 5 minutes. That's how long it would take me if I didn't need to share my screen. Okay, still doing it. Oh. Okay, so now let's do the plot and we'll describe the plot to you. Okay, so this is the plot. So let's understand this plot. So foundation that I have highly for you is you should read this particular PDF called qcnsimpleafi.pdf. As I told you, this is available once you download a package under your program files, R, library, SimpleAFI, and then the doc folder. So there are several concepts that this particular file tells you. The file tells you what is a background, what is a scale factor, um, and what are the different ways that AFI actually does the QC. So the four things you have to remember: one is a concept called average background, second is scale factor, three is number of genes called present, and a 3' 5' ratio for beta actin and GAFD genes, and some spiking controls. So let's try to understand this five concept in terms of our diagram. So in this diagram over here, you see a vertical line here, right, that I'm showing you. Okay, from this vertical line, you see a horizontal line that goes this way that ends with a dot. So in this particular cell file, that's the vertical line, and this is a horizontal line that goes here. That's the horizontal line that goes there. So what this horizontal line is called is a scaling factor. For you to understand in detail what a scaling factor is, I recommend that you read this, the scale factor here. So what it will tell you that when you do a mass 5 normalization or mass 5 summarization rather on an Affymetrix array, so for each array all the trim mean intensities are same. And we talked about trim mean intensity when we did our first task 1 in lecture 1. So if you have one array with 10 probes, let's say, that has a value from 1 to 10, then your trim mean, let's say, is 5, figure of speech, and you have another array from 11 to 20, and let's say your trim mean is 15. So what you're going to do is your second array, you're going to divide it by 3, so the trim mean of that is also 5. And your first array, your trim mean was 5 because it was 1 to 10. So in your second array, when the trim mean was 15 and you divided it by a 3, so that's the scaling factor. So that's how you do, because of that division, your trim mean now became same between your two arrays. So that's exactly what this particular thing is doing. The scale factor here is in a half a fold. This is here the scale factor. So this vertical line represents 0 fold change. But when you have up to here, that means 1 fold change. This is 1.5 fold change. So those are the numbers that you're actually dividing each of those intensities. So across the arrays, all the trim mean intensities are the same. So that's scale factor. When your scale factor is within the blue region, so you can have a scale factor that goes negative this way, negative fold change. You can also have scale factor for positive fold change. So the first dashed mark here is 1 fold change, this is 2 fold change, and this is 3 fold change. And you can see that from the scale here. So it's 3 fold change positive, this is 3 fold change negative, and 0 is your central line, and this is your scale factor. So as long as your scale factor is in the blue region, you're okay. That's the first concept. Second concept is you have some gene called GAFD and beta actin, right? So what they do in the AFI chips, they set probes at the 3' and 5' ends of the GAFD and beta actin. These are the control genes that you have to assess the RNA quality. So some of the control probes are actually targeting the 3' probes, and some of the control probes are targeting the 5' probes. But they're both targeting, even though they're designed for the 3' end or the 5' end, they're both targeting either the GAFD or beta actin. So the ratio of the GAFD 3' and GAFD 5' is indicated by a circle, and the ratio of the actin 3' and the actin 5' are indicated by by a triangle. So if your circles are also within the blue region, then you're also okay. So you're expecting that your GAFD 3' to 5' ratio would almost be one-fold more. So you have your zero here, or the circle. So the ratio of the same gene GAFD, but the 3' probe would be probably one-fold more than your 5' one. So as long as these particular circles are within your first fold change, you're okay. But say this one was between 1 and 2 or 1.5, so this is actually marked as a red. So that's not okay. And your actin 3 and 5 ratios are expected within 3-5 fold. So everything, all the triangles here, so this is 2-fold, you're okay. This is 2.1 fold, you're okay. But these are marginally just above 3. This is marginally just above 3. So these two particular cell files, the QC will not pass, because your actin 3 and actin 5 is actually on the borderline. So as far as QC and its protocol is concerned, it depends how your particular lab sets them up. So since in this scenario this particular two deltas or triangles are just marginally did not meet the criteria, so maybe you will have a procedure to say, I'm okay with this, I don't have to fail these cell files. But if this triangle was way over here, so around like 4-fold change, then you can probably assess to say it failed one of my QC step, so I'm not going to recognize this cell file as part of my analysis, so you can exclude it. But so now you understand what the red circle and the red delta meant, because it did not meet the expected ratio criteria of one-fold and 3-fold. Anything that's within the blue is okay. If you had a scale factor that went above the blue this way or went to the blue that way, then you wouldn't be okay. And you can actually also see that from your simple FE when you look at the diagram of your QC here. And if you notice, see, these are actually outside the blue zone here, so this is not acceptable. So that's why they have been marked as red. And on this end, if it's more than one-fold within even though it's in the blue zone, so they are also not acceptable. So anything that's red, that's not good. Anything that's in blue here, it's good. And the last two things that's over here, so this is called the percent of genes that's in your cell file that has been called as present. And this is the background correction. So what FAQC also says that your percent gene number and the background correction should be the same, pretty much roughly the same value, but here it's almost double. This is 32 and that's 67. That's why it's flagging this particular value in red. So all these criterias that goes on into your QC, what these different figures and blue zone, delta, circle, and these numbers are, you can actually find the details in your simple FE PDF file. It actually takes you step by step of the 4 different or 6 different parameters that I showed you, so you can read that. And in addition, I also recommend that you read the QC simple FE this protocol here, so that will give you even more detailed description than I have been able to, which is what is the background, what is the L factor, what you mean by percent gene present, what is the 3' and 5', right, which is the actin and GAFD that I just showed you, actin and GAFD that I showed you from plot. And finally is the housekeeping gene, which is in each of this FE array you expect that this particular control probe bio B will be less than bio C, the amount of bio D will be less than CREX, right? So this should all these control probes, the intensity of them should be in increasing intensity. So that's the plot. And in addition, if you need to find some additional details, please consult this PDF file and the QC simple FE PDF file. So that was the QC. The other thing I also wanted you to do that Okay, so I also give you a note here, right? So your this particular line is the zero full line. Then you have your first full, second full, and how the FE states that beta actin should be within 3. So this is fine, this is fine. That's a little more than 3, and the circle or the GAFD should be within 1. Okay. The second thing I wanted you to do is to draw a news plot, and for which you actually need the FEPLM package. FEPLM is another package that does a model-based QC. So the QC that I showed you here is coming from the simple FE, and I talked to you about the 6 different parameters that this QC package looks. But if you want to do a little more sophisticated QC, you get into the FEPLM on model-based. I don't get into the detail of the model-based QC, but one thing interesting that was in your textbook is you can actually do a news plot, right? So since you don't have, if you don't have this package to begin with, remember you have to do BioC Lite FEPLM to get the package, and then once you have the package, you load the library. So I'll do that. Okay. Then I actually fit a function here, called fit PLM on the raw data. And the raw data is the same data that I picked up from my expression set object. So I put the expression set object and I do a model, and I can get into that detail if you guys are interested to understand the fit PLM model. And again, apologies, it's slow. So I think it'll, since it's doing a model fit, it's going to even take longer than how long it took to read it. Okay. Okay, so now that's done. Um, in order for you to create a news plot, and I give all these other comments here, so when I post it, you should be able to look it up. So first you prepare a PDF file where you're going to draw it, and then you draw a box plot of news plot, and this is taken exactly from your book. And what does the news plot mean and what it stands for, you should be able to find it in the textbook. So I will not go into that detail. And it should get saved on your working folder, which is, if you go back to your R1 folder, which is your working directory, and at least in my scenario. So let's go and open that file and just take a quick look. So this is your news plot. So again, what you are trying to do with the news plot and with the FEPLM package is slightly different than the other QC that you did. It's a combination of things you probably need to do for your QC. So what the news plot in essence says, that you can take all of your cell files and the median intensity, right, as we were saying. So this is not using any mass5 algorithm, so I haven't forced the median intensity to be same. But what you can expect is the median of them should all line up pretty much. So if you look at these 5 cell files, the median intensities are pretty comparable. But these 3 particular cell files are actually, the median value or intensity is a little higher than the others. So you almost have one group here, another group here, and the last 3 group is here. Then if you use your mass5 algorithm, but in our case we'll actually do RMA, they should all like line up pretty evenly, the intensities. And that's something you are doing here before normalization, and after normalization you can do another news plot and verify that the median intensities across the cell files are comparable. So always like try to look at the picture and see, what does this delta and circle mean, what does the blue region mean, what are these numbers. You have to understand that, because if you do not understand and just issue code, I just don't see any point to that. And the second way also, once you create a news plot, try to understand what that news plot meant and what the next step needs to be. Okay, so now that we looked at some preliminary data, QC data at our expression set object, so now in our next pipeline, what we need to do in our raw data, which is the expression set object, I need to summarize, normalize, and background correct it using RMA method. So you can also use GCRMA method, you can use Maths5 method. So these are all the different methods available. But in your assignment, I'm requesting you to do it by RMA. So use the call dot expression to do that. And how do you know how to use call dot expression to begin with? Again, you can do that by issuing a help on your library equals to FE. On your simple FE.pdf file, this code is available. I also gave you hint in the homework, so in combination of those should help you to get to where you want to. So but again, we'll come to the pairwise comparison in a bit. So you did the QC, so now let's do the normalization, summarization, and background correction by RMA. And again, this is going to take a little bit time being how slow my laptop is. So you started with your raw data cell files, 10 of them, right? So you created a conf.tst, everything is in the R1 folder. You pointed R to look at the R1 folder. You imported the simple FE library. Once you imported the library, you created an expression set object by using the raw dot, I think the command was read.fe. Then once you have the raw data, we just did some QC on it, and now on the same raw data, we are now normalizing it by the RMA method. So that's what RMA did. First, it did a background correction. It normalized by using quantum normalization, and it summarized the expression by subtracting from the each of those normalized value for each probe set. It subtracted the subtracted the mismatch from the perfect match, and summarize for each probe sets. Now you have one value for each array. So up to that, you did that. So now you're going to do some pairwise comparison, which means that you're going to take each probe set at a time for each array, and you're going to group it by a condition. So you have 5 arrays that belong to lean condition and 5 array that belongs to the obese condition, right? So you're going to group the value of your 5 arrays for one probe set. So you have one value there, and you're going to compare for gene 1, let's say in your first 5 array that belongs to the lean condition, with the gene 1 on your second set of 5 arrays that belongs to the obese condition. So that's called pairwise comparison, because you're doing one gene at a time. So in that pairwise comparison, you're going to do a mean value between, what's the difference of mean, right? What's the mean of the value between at lean condition, and what's the mean value at the obese condition? Then what's the test statistics based on those means? Are the means significantly different? From the test statistics, you can also get a p-value result, assuming it's a normal distribution. So the way you would do the pairwise comparison, the code is already given here. You supply the normalized or processed data. You should not give the raw data here. In my scenario, it was x.rma, which is the RMA process data. You're going to tell the treatment, which is going to be the same as the column header that's on your conf.tst. So that gives you the factor, meaning lean or obese. So in this example is N or A, but if you look at the conf.tst, it was L and O when I showed you that, right? So in my scenario, the collection of L and O, and also you give the raw data to get the present absent calls, okay, and marginal. So in FE, always whenever it registers an intensity value for a particular probe set, it flags it as either present or absent or marginal. So that's your PMA call. So this was the syntax that was given on the help. So you do the same thing. X.rma is your process RMA data. Treatment is the header in your conf.txt. And let's just open conf.txt just for the sake of it. So this is treatment, right? And this is L and O. So in your particular case, it has to be exactly treatment, L and O. And raw data is what you read here at the very beginning, when you constructed the expression set object from read.fe. So that's your raw data. Raw data also comes with present, absent, and marginal. That's why you need that along with the RMA process data. So now let's do the pairwise comparison. So it's going to run each gene at a time and compare for 5 cell files that belongs with the lean condition with the 5 cell files that belongs to the obese condition for each gene at a time. Calculate what mean, calculate test statistics, calculate p-value, tell you whether the calls were present, marginal, or absent for each of those genes in all of those 10 arrays. I give you a condition is, it could be a gene that you did for the first 5 arrays you did the mean, and for the second set of 5 arrays you also did the mean, but that gene did not have a present call in all of the 5 arrays in the obese condition. Maybe it had a present call for all of the 5 arrays in the lean condition. So one of the things I asked, that make sure when you do that pairwise comparison and after when you filter it, that gene has to be present call across all the 10 arrays. You can also lower that threshold to say as long as it's present across the 8 arrays, I'm okay. But that's up to you. So if every time I do something in R and I use and invoke a particular method, it's my practice to understand what's the class of that thing that it just output. So if you look at the class of pairwise results, it's a class called pair comp. So what does pair comp again is? So if I look at the structure of it, that will give me a better idea. So it looks like it's similar to the expression set object. Started with class version, has protocol annotation, so still up to now it's the same, right? So on top of that, up to here, up to phenodata, I suppose, right? Right. So up to assay data, it's the same thing, but these are the new things that the pairwise result class extends on and builds on top of the expression set object. So right now, on top of your expression set object, you also have the mean, you also have the fold change, you also have the test statistics and the calls, which are present, absent, or marginal. So now, if you want to get the mean out of your pairwise result, you can say means, right? Pairwise result. If you want to get the fold change out of your pairwise result, you say FC pairwise result. So these individual commands that you have are going to able to extract for you the mean, fold change, test statistics, and the calls, which is this. So means, test statistics, fold change, calls. So what you want to do, you want to take the data out of this class, which is the pairwise class, pair comp class, and the class has different attributes, means, fold change, TT, and calls, and write that into a frame. So once you write that into a frame, it's very easy so it becomes, it's a reduced complexity object, right? So it's just a frame. So you can save it into an Excel file. You can easily extract an element or a column out of that frame by using the dollar or parentheses, etc. type of command. So it becomes much easier when you take data out of a little complicated class and put it into some of the basic object in R, like data.frame or matrix. So think of it like you start with basic objects like frame, matrix, and you build relatively a complex object. You do a lot of operations on that complex object, then you want to again filter down and bring that data back downwards into more simple objects like frame and matrix again. So you can manipulate the data, extract the data, massage the data, and etc. So that's exactly what you did here. Your pairwise comparison method actually resulted into a pair comp class, which is an extension of the expression set with this additional attributes or slots. So now you can reference to those individual slots and construct a data frame. And that's exactly what we do here. We get the means, fold change, and etc., etc., construct a data frame, and on top of that, we write it to a table, right? And we save the file as paircoms.xls, which is separated by tab. And now let's look how that file looks like. So now in my R1 folder, I should have a file pairwise.com.xls available, which is simply an export of this frame into Excel file. So now let's look at it, and I hope at this point it will make sense. It will be more clear to you, where we arrived and what we did by pairwise comparison. Sorry, some leftover from work. Okay, so this is what you actually did up until now. So you have your 10 cell files, right? So these are your 10 cell files. Your first thing, which is FC, when you did let's go back to R now. When you did your FC pairwise, FC, TT, right, calls and means. So each of those that you did, they all got saved here. You have your means here for the lean, means here for the obese. Then between those two mean, you did the fold change, so that got saved here. Statistics got saved here. Your right pairwise result from that, your mean, fold change, test statistics, and calls, all of them now you're able to see here. And whether it's present in all 10 arrays. In this scenario, this is absent in these arrays, and in all of them you didn't register a call. On this one, maybe present, this is marginal, etc. So all these calls are also coming along, and you are doing it pairwise because you're taking each probe set and you're comparing the two pairs. One is the lean and one the obese. So you get a single mean intensity for lean, single for obese. Then you subtract it, you get the fold change. Then you can calculate test statistics based on your normal distribution, and then these are your calls. So once you export the data and look at it, you can get a better visualization of what you just did. So this is your pairwise result. So now what we need to do, we need to do a filter. In my filter, what I am saying that from this table, give me only those where my test statistics is at least 0.01, right, or less, and my fold change is twofold, at least 1.5, and this is present in all the 10 cell files. So this condition will not be met because this particular probe set, first of all, doesn't have of a test statistics of 0.01 or less, doesn't have a fold change of 1.5 fold, it's only 0.11, and it's also not present in all 10 arrays because it's absent here and absent there. So what you have to do here is you have to go from your main object, paircom object, pairwise result to a filter one. And the simple FE already tells you, how to do this filter is by using the pairwise.filter function. And it's all in your simple FE.pdf. So you start with the pairwise.filter, right? So this is your main table, which is not a main data frame, which is nothing but this particular Excel file that I'm showing you. Plus you give the conditions that fold chills has to be this, it has to be present at 10, and the test statistics has to be minimum of 0.01. Okay, so once you do that, and your present by group is actually has to be true because it's sorry about that, because it's lean and obese. So your present by group has to be true because you have a grouping here, lean and obese. Okay, so now it's going to filter what's available on your from your okay. So checking member L in group and checking member O in group, and I hope I did the same thing there. Okay, so you already did that, so lean and obese, and your present by group has to be true, which you did. So now what you do the same thing. Let's look at the class of your pairwise, of your significant. It should be paircom, which is an extension of the expression set by those additional slots of fold change and present call and test statistics and etc. So still paircom. Look at the structure of it. And I intentionally do that because I don't want to do things blindly. So I want to have an understanding of what my object is, how it got created, right? It got created from my expression set, plus what additional items are available here. So these are the additional items available: mean, full chain, test statistics, etc. But by using this particular method, pairwise.filter, it starts with the pairwise.result. So you input that, then you give your condition that it's present by group, and has to be present in all 10 arrays, has to have a full change of 1.5, and then outputs only those significant ones that made the criteria, stringent criteria, in the significant. So now that you have that significant as a class, so you can just only refer to the mean, full change, and test statistics of that class, right? And write that into a frame, just like the way you did before, and export it into an Excel. And then you can see how many of them actually met your criteria. Maybe it will be 20 of them, maybe it will be 10 of them, we don't know. So we just did that, right? So let's look at the significant, and it has to be when a group by false. Okay, so actually when you did a group by false and none of them actually meets the criteria, group by true, right? So how about I do again, maybe instead of present call in all 10, maybe I do maybe 6 of them instead of 10. So it will check for the member in L, so make sure all 5 is there. Check for the member in O, it has to make sure all 5 is there too. And do I get? No, it's not giving me. Okay, give me a second. But if I don't check by group, it will give me a 20. Okay, so now okay, so I have to close the file here, significant, because when the file is closed I cannot write to it. I mean open, I cannot write to it. So let me close the file, and if I don't do it by group, I should get 20 of them that's present. So in this scenario, okay, so if I don't do the condition that the present has to be in all 10 arrays, but I just make sure that as long, so I get about 29 of them that meets my criteria, where the test statistics is less than 0.01, so these are very, very low test statistics, okay, and the full change here is minimum about 1.5, okay. So that's for 8. I think not all, I think I had 8. But how about I still do, it has to be present in all 10 of them, but I don't want to group it, present by group. So as long as they're in all 10, so I did that, and I think I should get 20 of them. And let me close the file that I just wrote for significant, so I can write to it. So that one I showed you for 8, but I think my homework I said 10. So again, we take the data from pairwise filter, the class, which is a paircom class, which is an extension of the expression set object with mean, full change, and test statistics. Then I convert that into a data.frame, write it into a table. So this time, if I open it for my significant files, I get about 20. So I get about 20 probe sets that with the lean and obese has a full change of 1.5, but log 2, sorry, log 2 1.5. Sorry, it's not 1.5. So log base 2 of 1.5, which meets this criteria. So all of these are less than 0.001, and they're all present in all 10 arrays. So they're all present. Okay. So that meets that criteria. And now if I want to show how many, the first 25, I may not have 25, I probably have only 20. And if I want to sort it by the significance of the test statistics, means the lowest statistics as first, so I have my probe set and these are my test statistics, which is the p-value also in this case. They calculate test statistics, but they're actually showing you the p-value here. Okay. All right. So now you have to draw a Volcano plot of your test statistics versus the full change. So on your Volcano plot, you need to understand few things. What goes on your x-axis versus what goes on your y-axis. So on your x-axis, you have to show the full change. And on the y-axis, you have to show the p-value and the log 10 of the p-value. So let's just first figure out what are my the full change and test statistics for my entire 10 arrays. Okay. So this particular significant one that I'm showing you here, significant, right? This is the class. So when I did a pairwise filter, that got stored into significant. So what does significant stores? Significant stores only your top 20 of them that you actually wrote on your Excel file. So if you look at your Excel file, significant only has 20 probes. So these are your top 20 that met the criteria that I told you to. But in your particular feature, you actually experiment, you had 22,000 features that you started with. So you have to calculate the p-values and test statistics for 22,000 features, and you also have to calculate the test statistics or p-value for your 20 features. And let me take you through that first. So for calculating the 20 features, let me write down, I'm sorry. Okay. So this particular line that I have for the significant, I did that. I wrote down into a table. I sorted it. And once I sorted it, I only see that I have 20 of them available. 21, 22, 23, 24, 25 is not available because I only got 20 such probe sets that met my criteria. And now I am just going to construct a frame. In this frame, I will store the mean, full change, and test statistics, and whether they are present or absent, only for the significant or the 20 top probe sets that I got out of my step above. So that's my top probe set. So if you look at my top probe sets, right? So this is a frame, and in this frame, what I'm storing is for 20 probe sets for lean and obese. These are the mean. I'm storing the full change and I'm storing the p-value. So that's just for the top probe sets. And I can actually sort it by the test. So if I want, so this is a frame, right? So out of this frame, if I only am interested in the test statistics, right, this column, so what do? I say $TT, right? Top probe set $TT will give me this particular column. And remember, dollar does a pattern match, so I don't have to say exactly TT dot significant dot etc. As long as I say top probe set $TT, that only gives me this particular test statistics, this column. So what I'm going to do is I'm going to store my first 20 test statistics or p-value or whatever you want to call it into this variable lowest t-value probe sets. Okay. So if you now look at lowest t-value probe sets, it should only have the test statistics values. So I went from a frame and I constructed the frame purposely so I can actually just extract out the test statistics or p-value that I'm concerned with. So those are just for the significant one. And now I need to make a switch where I need to get the test statistics for all of my probes and p-value for all of my probes. So in order to do that, I actually go and pairwise result was something that came. This pairwise result, this did not have any filter criteria, right? So this will still have the 22,000 probes with their means and fold chains and test statistics and etc. So significant happened to be the first 21. But from pairwise result, I can get the all 22,000 that I want. And the way to do that is, so t-test for the entire probe set. So if I look at the pairwise result values, and pairwise result values I saved as a frame over here. So on that frame, I am getting the mean from the pairwise result, right? And again, this connection you can make from the pairwise result here, which is, this is the pairwise result. It did a pairwise comparison between lean and obese. So this has actually all the 22,000 features across your 10 cell files in the samples. So this has nothing to do with the top ones. So I take that class and I actually construct that, only taking the portions of the means, fold chains, test statistics, and calls over here, right, as a frame. So once I make a frame, I can actually refer to just the test statistics portion of it. So that becomes the frame. If you want to look at the top of it, so let's just do this one, so you can visualize how this frame looks like, the first 10 rows or so. So if you do that, so now you can see for the first 10 probe sets, this particular pairwise result value will contain all the 22,000 probe sets that you have. The significant one that you did, right, which is the lowest t-value probe sets, that actually contains the probe sets of first 20 that happens to meet your criteria. This one will have all of it. So what you want to do now is, out of this pairwise result value, if you do a $TT, you will get this value for all 22,000 of your probe sets. And that's exactly what I do. Pairwise value results, $TT. So if I do that, so this is my frame, pairwise result value. If I do a $TT, then I will get this exact column. And that's what I do, and I store it into the all t-value probe sets. So now if you look at all t-value probe sets, it will give you all the way up to 22,283 probe sets t-value. So that's the picture you have to think. In one variable, you have to store the 22,000 probe sets t-value, and another variable you have to store the t-value only for your top ones. So this is your test statistics. You can also get the fold change the same way. Going back to pairwise result value here. Going back up again. So in this case, you got the test statistics here, and you got 22,000 of them by doing pairwise result value $TT. Now if you do pairwise result value $FC, you should get the fold change for all 22,000 genes. So I stored that in this variable called all fold change probe set. All I do is pairwise result value $FC. So $FC, because of pattern matching, will give me this column. $TT, because of pattern matching, will give me that column. Okay. So key here, again, I cannot emphasize more. Get all the t-values for all probe set. Get the fold change for all probe sets. And what's important here is only the t-value for your first 20 probe sets that came up from your criteria that I gave you for present in 10 and tested as a p-value at least 0.01, etc. So now that I know all my t-values and all my fold change, what I do, I want to plot the fold change in the x-axis, and I want to plot the p-value on the y-axis. And what I want to do is I want to take a log 10 of the p-values. That's how it shows on your text also. And now you can plot your fold change, which will be on the x-axis, right? And your log, which is the p-value, the log 10 of your p-value, which is with the y-axis, is the same as that. I assigned it to log. and the X label will be fold change, and Y label will be the log of your of your p-value, locked in of your p-value. This is just a label, it's not a function or anything, so don't get misled by this. So let's do the plot now. So that's what the plot looks like, the initial Volcano plot. So in this Volcano plot, you have a lot of dots. So these dots represent all the 22,000 probes that are in your experiment across the 10 cell files. On this x-axis is the fold change for all of your 22,000 probe sets FC, and this is the p-value for all the 22,000 probe sets FC. So you get all fold change probe sets, $FC. This was your x-axis, this was your y-axis, and what you did on top of that, you took a log 10 of it. Now the key of this assignment is I have this shows me the 22,000 probe sets, fold change here, log here. So the key here is how do I now spot here and show the top 20 probe sets that showed up based on the low p-value. So what is an ideal is you have a very high fold change, which is sort of over here, right, like this point, and a very low log low p-value, and then this one is a very good point, which is you have sort of a high fold change and a very low p-value. Remember in the last lecture I told you that with biologists there's always a compromise, that if you want to look at the fold change, then you compromise on the t-test or p-value, and if you look into the p-value, then you lose the power of the fold change. So that's why sometimes you want to do this kind of Volcano plot to say, these are the points that are probably interesting because it meets the criteria of a high fold change. It also meets the criteria that I have a low p-value. This particular point can have a very high fold change, right, over here like 1, but the test p-value is so high that it's probably happening just by chance, or that was the whole reason we went into p-value, test statistics, normal distribution, all these things we talked about in the last few lectures. So even though these points have very high fold change, but because of high p-value, it's not of interest. These ones may have a very, very low p-value right over here, but it has a very insignificant fold change. Anyway, so enough said on that. So we have 20 points, right, which showed up as our lowest test statistics or p-value here. So how do I plot those? So remember, I saved the lowest p-values on this variable, right, which has the value of those 20 test statistics. So now what I need to do is I can save it, the values of them, into a variable called O1. So if you look at O1, it's the same, those 20 of them, okay? And I can actually subset those O1. So my all t-value probe sets, right, if I just control that one, has the test statistics of all my 22,000. So if I subset with the O1, it should return only those 20s, right? Oops. So it should return only those 20s, and then I can take my log of that also, which is the low of your all t-value presets, and then now if I execute this code, oops, I think I did not do something correctly here. Okay, so I did that, and did that, and here. I think it's getting printed somewhere else. So let me do that one more time. So my all t-value test sets, these are my all fold change, and I convert it to a log, and then if I print it, so that means my fold change is here and my other one is there, and I want it to the lowest. So I want to subset only the one that's applicable for the think I not doing something right here. Okay. Lord O1. Okay, give me a second. Today hasn't been a good day. It's been a lot of obstacles. So this should be an exercise 3.6, right? So PCH is 18, color is blue. I think I am missing something here. And give me 1 second. I think I may have mistyped something here. Where's my... Did I overwrite something? Okay, so I think I did not do this. So if I order it, because I was just playing around with this one. So if I order it, points, okay. So let's do this again. Forget, okay, so this is where the points are. Okay. All right, so we did that. So let me clear everything and redo the whole thing so you guys can again follow it. Clear console, edit, clear console, clear everything, file, open script. So let me do that for 5 more minutes and we'll end at 8. So you can follow the entire solution and I'll go very fast, maybe 5 minutes. So let's just do this. This is the new script. So first I set my directory, right? I did that. I load my library. I did that. I read the files, creates an expression set object, takes a minute or two, let it do that. It's okay. So now this file got created. Let's do the QC on this raw data. So we'll do that. So now let's plot it. So now you know what this blue region means, what this vertical means, delta means, what circle means, what fold change means, and what this present call versus this is the background ratio means. So I also told you the file to look up, right? Read this one, qc.simpleafi. Not going to go through the simple the news plot, very simple, you can do it yourself. Let's take the raw data, input this into this function, use the RMA method to normalize, summarize, and background correct. I wanted to do the clustering, which is a huge topic, but it's not going to happen today, so I'll follow up with another meeting note. Maybe next Sunday we can do that, or Monday. In my case, it's L, lowercase l, and lowercase o. So I'm going to do a pairwise comparison. This function is already there for you. You need the raw data for the present, absent, and marginal call. This is the output of what you did with RMA. So each gene is going to get compared one at a time by this grouping of L and O, right? So that will get saved into a pair comp class, which is an extension of the expression dataset object with additional, other than the assay data, pheno data object, you have the additional fold change, test statistics, mean of those values. So once it does that, now I'm going to use and write it into a frame, and you can export it into a table and etc. But I'm not going to repeat that here. So you're going to now filter it based on the condition that log of the fold change value of 1.5 or whatever log that is, 0.6, and at least present in 10, and I have a p-value. In this case, it's the same as test statistics, they call it, but it's the p-value they are calculating of 0.01. So you're not going to get that many. So that's your significant. So you have to differentiate between pairwise result and significant. So from pairwise result, what you're going to do is you're going to get a test statistics and p-value for all of them, right? So what you're going to do here is your top, you have to get your low, okay, so you can do that and export in Excel, so it's not important. So for your top probe sets that you have to, you're only concerned about the 20 that you got from significant, right? So significant is the pair comp class. So what I do here is I save it into a frame, data.frame, so it's easy to access it by using the dollar command. And then I only get so if you look at your top probe set here, and if you look into the head here, right? So if you can do top probe sets $TT, that will give you all the test statistics that you want. So that's what I do here, $TT, and you sort it decreasing from 1 to 25. You will only get 20 of them. So I store my t value for the significant ones here, and now my pairwise result values.tt that came from this one, pairwise result, right? So this one, I want to get the test statistics and fold change for all of them. So let's do that again. So this is just for the significant one, and I want to construct another frame that will, this particular frame I constructed above only contains the values for the top 20 genes. This particular frame that I'm constructing should contain the mean, fold change, and test statistics for all 22,000 genes. So that's the frame. And once I got the frame, let's extract out the test statistics for all probe sets. Let's get the test statistics or fold change for all probe sets. So that's all, fold change, all t-value, lowest t-value. So these are the three parameters that you need for your plotting. You convert the p-value or test statistics into a log 10. That's how the plots are shown on your book. Now you're going to plot on your x-axis the fold change. Let's get rid of that. On an x-axis, the fold change. The y-axis, the log of the p-value. These are your labels. So that's pretty simple. So you do that. So that's your Volcano plot for all 22,000 probe sets, and I explained what Volcano plot is. Now the last point is putting a dot with a blue, the top 20, wherever it belongs, probably somewhere over here. So the way we do that is we take the all t-value probe sets, right, and we sort the first 25 of them, which is the first 25. If you sort it, I'm only interested in the first 25 of them, and then I want to plot it. Okay, and that's what it plots here. So that's the solution of homework 2, and I apologize for a lot of the delays and roadblocks that we had. Maybe after I subscribe to